Hi there. So today we're going to talk about chapter 6, 6.1. We're going to finish it up. We've already talked about discrete random variables. Now we're going to talk about continuous random variables. And everything we're going to talk about today is going to sound very similar and feel very similar to chapter 2 when we talked about continuous density curves and normal distributions and all that stuff. We're just going to be kind of, a lot of the calculational things are the same. All the calculational things are the same. We're just going to be kind of interpreting our answers differently, and the question is going to be asked. We'll be answering a different question. So let's get started. A continuous random variable we've already talked about a little bit, but it can take on any value on an interval. So there's basically an infinite number of, responses, as opposed to like a discrete random variable. We can't make a probability distribution table where we have like specific values of x. X could be either 0, 1, 2, or 3, and find the individual probabilities because it's continuous. So we think about our continuous random variable as being a density curve, and we're talking about like the area under the density curve. And a couple key things here for density curves. If you remember back to chapter 2, density curves have to be entirely above the horizontal axis, and their areas have to sum to 1. Now think about this in terms of like random variables, right? If we sum up the probability of all possible outcomes, the sum has to be equal to 1. So this all kind of should line up and make sense. And again, we're like bringing everything together. So here's an example. If I randomly generate a number between 0 and 9, and if I define y to be that randomly generated number between 0 and 9. So it's a continuous random variable because I didn't say a randomly generated integer, right? We said a randomly generated number. And so each number has equal probability of coming out. And if you think back to chapter 2 with density curves, if I asked you to draw this density curve, you would say, okay, well, I know that the area under the purple density curve has to be equal to 1. And so if this distance along the x-axis is 9, so the area is a rectangle, so 9 times what gives me 1? So the height has to be 1/9, right? And the shaded area represents the probability that y is between 3 and 7, for example. So if I were to ask you what's the probability that you select a random a random number between 3 and 7, you would find the area of this green shaded region. So you would say like 1/9, because that's the height, times the base, which is 1, 2, 3, 4. So that area would be 4/9. In chapter 2, we asked questions using density curves, but the questions were something like this. What's the probability, what percent of randomly generated numbers are between 3 and 7? And you would say, 4/9 of them. Now we're going to ask a very similar question, but instead of the one we just asked, we're going to say something like, if I randomly select one number, what's the probability that it's between 3 and 7? And so the answer is still going to be the same, 4/9. Okay, so again, there's an infinite amount of values, so we can't assign individual probabilities. So I can't, for example, find the probability that y is equal to 3 in this example that we just looked at, right? So therefore, if you look here, the probability that x is less than 8 is equal to the probability that x is less than or equal to 8. That's not true in a discrete random variable, though, because I can find the probability that x equals 8 in a discrete random variable. But in a continuous random variable, this is what I have. Okay, so let's look at an example. Take a minute, read this. All right. So the probability of Y, and Y is the amount of time that it takes her to get to work by train. So the probability distribution of Y can be modeled by a uniform density curve on the interval from 2 to 5. So find the probability that it will be quicker for Selena to take the train than to walk that day. So what we would think of is, we would think of our uniform density curve, right? And we would say that her journey time takes between 2 and 5 minutes. And so the area under this curve has to be equal to 1. So the area has to be equal to 1. The distance in the x-axis is 3, right? So what would that make the height? It would make the height 1/3. So we're saying that the new walkway would allow her to get to work in 4 minutes. That's marked off here, right? So what's the probability that it would be quicker for Selena to take the train than to walk that day? So quicker to take the train. All these x times here are her taking the train. So if it takes her 5 minutes on the train, that's no good, right? That's longer. 4.5 minutes, that's longer. So all of this area, the graded area here, would be where it takes Selena less than 4 minutes to take the train, right? So if we want that area, I can take the base times the height. So the distance here is 2. The height, as we said, is 1/3. So that probability is 2/3. So in other words, the probability that Y is less than 4 is equal to 2/3, or 66.7%. In other words, if I interpret my answer, there's a 66.7% chance that it will be quicker for Selena to take the train to work on a randomly selected day than for her to walk. So we asked you questions like this, again, in chapter 2. You could have been asked a very, very, very similar question. But in chapter 2, it was find the probability that, or what percent of the time would she take quicker on the train. Now we're saying, if I pick to kind of interpret this further, if I pick like a random day, what's the probability that it's going to take her quicker to take the train, or a shorter amount of time to take the train than to walk? Okay. And again, we're going to use kind of everything that we learned from chapter 2 and apply it to normal distributions as well. So the heights of young women can be modeled by normal distribution with mean 64 inches, standard deviation 2.7 inches. Suppose we choose a young woman at random and let Y represent her height in inches. Find the probability that Y is between 68 and 70 inches. We've done this before. So you have to draw and label your curve, right? And then you can either use the calculator or you can use your z-table. So if you find z-scores, here's your 2 z-scores. And then if you use the table, you would subtract those values because you want this area in between those 2 cutoff scores. Or you can use your calculator. If you use your calculator, please don't forget you're using normal CDF, but then you're labeling your inputs, right? Don't forget to label your inputs. And you'll get the same answer, or you might be off by a teeny tiny bit, and that's okay. So if we interpret this value, the probability that a randomly selected young woman has a height between 68 and 70 inches is about, 5.6%. So in chapter 2, we were asking what percent of women have heights between 68 and 70 inches? And you would say, 5.6% of all women have a height between 68 and 70 inches. Now in chapter 6, we're saying if we select one woman randomly. So suppose we choose a young woman at random. one woman, what is the probability that her height is between these two values? We're essentially asking the same question. So in other words, we can use, let's like revisit notation. We can use normal distributions to represent continuous random variables. So notation, capital letter N, and then in parentheses, you'd have the mu and the standard deviation. That means that we have a normal distribution with a specific mean and a specific standard deviation. So in this case, we could say that if I define y to be her height, y to be her height in inches, I could say that y follows a normal distribution with mean 64 and standard deviation 2.7. So that's kind of the notation to represent this situation. So I can then standardize all of those heights. Remember, we talked about standardizing, calculating z-scores. So the standardized variable z is a standard normal random variable having this distribution. So if I were to say, okay, now let me take all these women's heights and standardize all of them, convert them all to z-scores, my new mean would be 0 and my new standard deviation would be 1. And we're going to revisit that kind of a lot more in the next rest of the chapter, but that's all you need to really know right now. And then that is it for section 6.1. Thank you so much for watching. Have a great day.